3D geometry and maps in 3D, looking at chapters 8 and 9 in practical linear algebra. Do some practice problems. So let's just start with a simple vector norm kind of question. What's the norm of the vector r, given by 4, 2, 4? And what's the length of 2r? So hopefully you remembered that a norm is just the length of the vector, or the sum of the squares of the items in the vector. So in this case, for the vector r, we have 4 times 4 plus 2 times 2 plus 4 times 4 is 36. The square root of that is 6, and so we have the norm of r is equal to 6. You could do 2r by multiplying it by 2 and working through that, or just having remembered that the norm is a linear operator, so I take 2 times r, take its norm, I just get 2 times the norm of r, which is 2 times 6 is 12. Okay, let's do some geometry with them. What's the angle between the vectors v and w? Think of the general form, don't just play with it sort of graphically in this case, and then come up with an answer. Okay, so in general and in dimensions, I can always figure out the cosine of the angle between two vectors is easily found because using the dot product formula, we know that cosine of theta is equal to v dot w divided by the norm of v and the norm of w. V dot w in this case is 1. 1 times 1 plus 0 plus 0. And the norm of v is 1. The norm of w is the square root of 1 plus 1 is square root of 3. Sum of the squares square rooted. So the cosine of theta is about 1/3, 1 over the square root of 3, sorry. So you can stick that in your calculator and do arc cosine and figure out that the answer for theta is around 58 degrees, or you could just sort of just leave it as the arc cosine of 1 over the square root of 3. So now let's look at an area problem. I'm going to actually draw this one slightly differently just so you get used to the fact that these can be done in lots of different coordinate systems. So here I've done sort of physics notation. Given that v is equal to 2i plus j plus 3k. This is ijk coordinate system, sometimes used in physics. We're going to take v and w, and we want to know what's the area of the parallelogram that has those two as edges. Okay, so hopefully you remember that the parallelograms, the area of the parallelogram is just given by the cross product, which especially in physics notation is something you've probably seen or will see. So here we're just going to take the cross product. So we get for I 1 times 2 minus 3 times minus 3. So we get 2 plus 9i. We also then get for j, we get 4 minus 3j. And for k, we get 6 minus 3 times 2 and 1. So altogether we get 11i plus 7j plus 5k. And then the area of the parallelogram is just the magnitude of that vector. So we take the cross product, take its magnitude. So we get the square root of 11 squared minus 7 squared plus 5 squared, which is the square root of 195, which I would just leave that way. You could calculate it with a calculator if you want. Okay, so now let's play with points and planes. What's the point normal form of the plane defined by these 3 points? So we have the point P, Q, and R. What is the point normal form of that plane? So to do this, solve this problem, we would choose one point as our base and then use the other two to get the normal. So we're going to choose, in this case, the point P, say it's on the plane, and then we form the 2 vectors, Q minus P and R minus P. Those 2 vectors, we can take the cross product to get the normal to the plane. Now in this case I used P, Q minus P, R minus P. I could have actually used Q and then done P minus Q and R minus Q, or I could have chosen R. All 3 of them will give us the same point normal plane when we get done, but because the points are different, the actual formula will look a little different. So in this case, we now just need to do the product of Q minus P, which is the vector 1, 1, 0, crossed with the vector R minus P, which is 4, 2, 3. Right? This minus P, so we just changed the last item. Doing that cross product, hopefully now you've gotten cross products down. I'm not going to go through the math, the algebra for that. We get 3 minus 3, 2. And hence the point normal form of our equation is given by 3 minus 3, 3. That's the n dot which is just matrix products. We have the transpose here, x1, x2, x3 minus 1. And this last is actually x1 is actually x minus p, but p is just 0, 0, 1, so we just end up with the last item down here. So this is n dot x minus p, the quantity, equals 0. And then I can simplify that and put it into a normal equation of 3x1 minus 3x2 minus 2x3 minus 2. This is not normalized, but it's at least an equation for the form. So now we want to go a little bit farther. Let's say that we want the distance from the origin to the plane defined by those points. Okay, so we just use the same plane. So hopefully this will be quick for you to get the answer. How far is that plane from the origin? Okay, so to get that, we have to go from the implicit form. We have to go to the implicit form and make sure that we have unit length normals. So we want to take 1/3 times the equation. So we're reducing it by its normal. So we have 1/3 times 2x1 plus 1x2 plus 2x3 equals 2/3. Multiplying both sides through, then we get that our plane's distance, which is on the right-hand side, is now 2/3. That's how far it is from the origin. Okay, so let's go the other way around and find an intersection. Given that P2 is a plane given an implicit form by this equation, and L be a line that goes through the point Q and has direction V, so this is a 3D line. Starting at that point, going with this as its direction vector, find the intersection of P2 with the line. Work through that problem, come back and hit play after you've solved it. Okay, so hopefully you have your solution now. Let's see how, check through it as we go through it. So the first is, we can view our line L as being expressed by -1, 2 times t plus 0. That is Q plus t times v. That's just writing that out, but putting it into a vector itself, where t is the parameter where we're going to go out. Now, since the line has to intersect the plane and we have the implicit form of the plane, we know that we can just stick this point, -1, 2 plus t 0, into this equation. So x1 is -1. We're going to take 2 plus t for x2, which means we multiply by 2. We get 4 plus 2t. We're going to take 0 times 2, 0 for x3, so we get 0 here. That item disappears. And then -1 equals 0, so I've already just put the -1 on the other side. If we look at that, we can then just rearrange it, take all the constants to this side. We get that 2t equals -2, therefore t equals -1. And we can verify by putting in t equals -1 to this. We get -1, comma 2 -1, so we get -1, 1, 0. We put that in here, -1, 1, 0, -1 gives us 0. So we verify it's actually on the plane. So that gives us our point of intersection. Okay, another intersection question. Let's ask, does the ray or the line P plus TV with P equals this and V equals that intersect the triangle with vertices given by these 3 points? Here I've used the word ray. In graphics, we'd want to make sure that the value of t is positive, so we're on the positive half of the ray, but other than that, it's just the same as doing the intersection with a line. So go ahead and work through that problem, see if you can figure out the solution. Okay, welcome back. Let's look at how we solve this ray intersection with a triangle. It's a little bit more complicated because we want to know where we hit the triangle. We want to make sure we're inside, so we're going to represent the parametric form of the plane containing the triangle. So if we go back, right, we have our points 3, 0, 0, 0, 2, 1, 2, 2, 3. We're going to take that. We're going to get our 3 points, a point plus u times that point minus one of the other points of the triangle, and v times, again, the triangle's other points. So we have 0, 2, 1, -3. So we get -3, 2, 1, and we subtract 3 over here. We get the same kind of thing. So this is the parametric form of our plane. And the intersection then comes down to finding a value for u and v and a value for t, which is our ray, such that these 3 things are equal, because the ray has to hit a point that's in this representation. So in this case, we actually have three rows. which gives us a 3 by 3 linear system. Minus 3, 1, 1. Minus 3 came from U. Minus 1 came from V. The minus 1 here came from the T, because I have to put the T on the same side as the U and V. So sort of subtract that, put it on this side, put the constant over here, and then I get 3, minus 1 minus 3 gives me minus 4. So now you can sort of see how I rearrange that to get this 3 by 3 linear system. Now I can use Gaussian elimination or any of the other techniques to solve that linear system, and I'll get the answer that UVT is 0, 1, and 3. And now that tells me two things. So U is 0, V is 1, and T is 3. So I'm 3 steps along the array, so I'm on the positive side. And U is 0, V is 1, which means U is 0 means it's actually on an edge. V equals 1 says it's on this on the edge of the triangle. So it's actually on the edge connecting these 2 points. So that'll tell me where it hit the triangle. In this case, it just touched the edge of the triangle. Let's do another intersection problem. Let's find the intersection of 3 planes. So I have the plane x1 plus x2 equals 1, x1 equals 1, and x2 equals 4. So you can sketch this out and solve it as well, but I want you to try and do it algebraically, because in general, you can't always visualize them well enough to figure out exactly what the answer is. Okay, so as I said, it's pretty easy to sketch it. I'm going to skip the sketch in this case because my drawing's not that good, but you can, let's do the algebra. So in this case, we want to build our linear system, which is 1, 1, 0, and it's 1, 1, 0 because we have 1x1 plus 1x2 plus 0x3s equals 1. Our next row is 1x1 plus 0x2 plus 0x3 equals 1, and our last row is 0x1 plus 0x2 plus 1x3 equals 4. So this is the general 4 by 4 matrix. Again, we can solve that one using Gaussian elimination or just do a little bit of row fiddling, and you can sort of get your answer is 1, 0, 4. So that gives us our point of intersection. Okay, let's do another, well, rather than intersection, in 3D, 2 lines don't actually have to intersect. So if I have 2 lines, they can be askew, and then we can ask, what's the point of closest proximity? How close these lines get to each other? And what's the point of closest approach? So I have here 2 parametric forms of my line, a point plus a scalar times our 2 different vectors. And in this case, I want to go ahead and solve it. So think about how you solve that. Come back after you have a solution. So to solve this, we're going to drive the formula generally, because I just don't want to just jump to it. This is one question that got asked in class. So here we have our first line, and I've just put in P and V to sort of keep it in general form. Every line is P1 plus S1 times V1, just general values. But since we're looking for the point of closest approach, or the points of proximity, if I let X1 be the point on line 1 that is closest to this line 2, and X2 be the point on L2 that's closest to X1. So I'm now going to say these are the special points that are closest. If I connect those 2 points with a line, it has to be perpendicular to both lines. Why? Because it's the point of closest approach. So whenever I'm talking about something closest to a line, it's always perpendicular. So it's got to be closest to both line 1 and line 2, which means I can take x2 minus x1, and if it's perpendicular, that line, x2 minus x1 is the line, dotted with v1, the direction of the first line has got to equal 0. Do the same thing with v2, and it's also got to equal 0. So this is just a general constraint for the points being the closest. Now, if I fill in the algebraic form of x1 and x2, I will get p2 minus p1 dotted with v is equal to s1 times v1 dot v1 minus s2 times v1 dot v2. And similarly for the second equation. And now I can go back to my actual problem and fill in the values for p1, p2, v1, and v2. And I'm going to get 0, 1, 1 dotted with 1, 0, 0, which is 0. And on the right-hand side, I'm going to get s1 dotted, well, v1 dot v1 is just 1. And v1 dot v2, you go back and look at them, you'll see their dot product is 0. And so that gives me 0 equals s1 times 1. The second row, I subtract them, and now I'm going to get, because I'm doing p1 minus p2 times v2, I get 0, 1, 1 dot 0, 1, 0. This time that's equal to 1. And on the right-hand side, I get S1.0, because again, V1.0, V1.V2 is 0. And then we get minus S2.1. So that gives me my solution. S1 equals 0, S2 equals minus 1, or minus 1 equals minus S2. And now I can put those back in the equation, and I get that the points of closest approach are 0, 0, 0, and x2 of minus 1 is 0, 0, 1. You can go back to those lines, and graphically, if you want, check. Those will be the 2 closest points for those lines. So lots of intersections and geometry issues we got through here. Hopefully this was easy enough for you to follow. If not, take some practice problems out of the 2 chapters and see if you can work through those until you're comfortable doing all these without looking too much up in the book. At least you have it in your notes.